Hello and welcome to 10.9 Convergence of Taylor series. So in this lesson we're going to be looking at the convergence of Taylor series, and we're going to try to estimate the remainder in a Taylor series. So we have our typical theorem for the Taylor's theorem. It talks about our Taylor's series where we have first derivative, second derivative, all the way up to we have this term here, the n plus 1th derivative. Okay, that n plus 1th derivative, that's going to be our remainder function. So if you look at Taylor's formula over here, we're expressing that remainder theorem, remainder term as this term. Okay, so where c is some value between a and x. That r sub n of x is known as our remainder of order n. And in other words, it's known as the error term for the approximation of the function by the Taylor polynomial over some interval. This theorem was from 10.1, just as a reminder of some of the sequences that converge to the limits. Okay, so some of these pop up from time to time, and it's a good reminder of which ones do that. Okay, in the upcoming example, we're going to be looking at this one in particular, number 6, where the limit as n approaches infinity of x to the n over n factorial is equal to 0. Okay, so just a heads up. So let's take a look at and we say that if the remainder function as n approaches infinity, if that approaches 0, then we say that the Taylor series generated by f at x equals a converges to f on the interval, and we write our function as our Taylor series function. Okay, so example 1, show that the Taylor series generated by f of x equals e to the x at x equals 0 converges to f of x for every real value of x. Okay, so we know that the function has derivatives, right, of all orders. We did a problem like this in the previous section. We showed that e to the x is equal to 1 plus x squared over 2 factorial plus x to the n over n factorial plus, we're going to say, some remainder of order n of x. And so now the remainder function, we're going to say that is equal to e to the c over n plus 1 factorial times x to the n plus 1. And then c has to be between 0 and x. Okay, so what we want to show then is if the limit as n approaches infinity, I'm going to point out this piece to you guys. If we have this x to the n plus 1 over n plus 1 infinity, we know that this is equal to 0, and that's from that previous slide where I showed you guys from Theorem 5 in section 10.1, right, that the limit of x to the n over n factorial is equal to 0. So therefore we could say that x to the n plus 1 over n plus 1 factorial is equal to 0 for every x. And since this remainder function equals 0, right, as we have up here, if the remainder function approaches 0 as n approaches infinity, then we could write our function as what we have up here. Okay, so our function here was e to the x, so we could say e to the x equals, and this was x to some, we got summation, let's say k equals 0 to infinity. This will be x to the k over k factorial, and this is equal to 1 plus x squared over 2 factorial plus x to the k over k factorial, and this continues. Okay, so let's take a look at the remainder estimation theorem. So for a remainder estimation theorem, they tell us that the absolute value of the remainder function of order n has to be less than or equal to the maximum value for all t values between x and a times we have this quantity x minus a to the n plus 1 power over n plus 1 factorial. Okay, if this inequality holds for every n, and the other conditions of Taylor's theorem are satisfied by f, then the series converges to f of x. So let's take a look at example 2 to show that the Taylor series for sine x at x equals 0 converges for all x. Okay, so for sine of x, let's remember its derivatives. So f of x is sine of x. F prime of x is cosine of x. Okay, second derivative of f of x is negative sine x. Derivative of negative sine x would be negative cosine x. Derivative of negative cosine x will be sine x, and we will be back to our sine x. So if we continue this pattern, every even derivative, right, is going to alternate between sine and negative sine. So we would say f, and we have an even number there for the derivative. Every even derivative is going to alternate between a positive sign, negative sign. So basically we're going to have negative 1 to the k times sine x. And then every odd derivative, first derivative, third derivative, they're going to alternate signs between cosine x and negative cosine x. So we would say f to the 2k plus 1 of x is going to alternate between negative cosine and positive cosine. Okay, so because we're at x equals 0, when we plug in 0 into these signs, right, at sine of 0, we get 0. So we know that f to the 2k of 0 is going to equal 0. And then when we plug in 0 into these cosines, these are going to turn into, well, cosine of 0 is 1, so these are going to turn into either 1 or negative 1. So when we do f of 0, this will be negative 1 to the k. So we notice that all the even power terms are going to turn into 0. All the odd power terms are going to turn into negative 1 or positive 1. So our Taylor's theorem will turn into x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus, and this will keep going, we'll have negative 1 to the k times x to the 2k plus 1 over 2k plus 1 factorial plus, and we'll have a remainder function, remainder 2k plus 1 of x. Okay, so now all the derivatives of sine x have absolute value less than or equal to 1. Okay, so because of that, we could say that m is equal to 1. And so we're going to use the remainder estimation theorem when m is equal to 1. So we would say absolute value of r 2k plus 1 of x is going to be less than or equal to 1 times, this will be x to the, now we usually have 2k plus 1, so if we add 1, that'll be 2k plus 2 over 2k plus 2 factorial. So now by that same rule that we used before, Theorem 5, Rule 6, again, I'll go back to it. Theorem 5, Rule 6 tells us that if we have the limit as n approaches infinity, x to the n over n factorial, it's going to equal 0. Okay, so keep in mind that limit as k approaches infinity of absolute value x to the 2k plus 2 over 2k plus 2 factorial equals 0. So this tells us that the remainder function of x approaches 0, and the Taylor series, or in this case Maclaurin series, because we're centered at x equals 0, for sine x converges to sine x for every x. Right, so we could say that sine of x is equal to summation k equals 0 to infinity of -1 to the k power times x to the 2k plus 1 over 2k plus 1 factorial, which is equal to our x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus so on and so forth. So let's take a look at our next example with the cosine. Show that the Taylor series for cosine x at x equals 0 converges to cosine x for every value of x. So if you remember back to our previous lesson, we already did the example for cosine x. And we showed that cosine x equals 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial, so on and so forth. We would have the alternating signs, -1 to the k, and then we had all the even powers showed up because the odd powers turn into the signs, and those are the ones that became 0. So we have the even powers, so x to the 2k over 2k factorial plus, we'll say the remainder function of 2k. Okay. So we say that because the derivatives of the cosine have absolute value less than or equal to 1, then we could use the remainder estimation theorem when m equals 1. So we would say absolute value of r 2k of x is less than or equal to 1 times x to the 2k 2k plus 1 over 2k plus 1 factorial. Okay, and so we see that we use the same theorem that we used before, right? We know that this quantity is going to go to 0 as k approaches infinity, right? So therefore the series converges to cosine x for every value of x. Okay, so we would say cosine x is equal to summation k equals 0 to infinity of -1 to the k x to the 2k over 2k factorial, which is equal to 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial dot dot dot. Okay, so let's take a look at our next example using Taylor series. So we could use Taylor series and perform operations of adding, subtracting, multiplying. These are all valid operations, okay, on the intersection of their intervals of convergence. So we could use operations like these to figure out the first few terms of a Taylor series when they give us problems of combining these functions in certain ways. So in example 4, it says find the first few terms of the Taylor series for the given function by using power series operations. Okay, so for the first one, we have here 1/3 of 2x. So we're doing a. So that means we would have 2/3 x, if I distribute this, plus 1/3 x times cosine x. So now I have 2/3 x plus 1/3 x. Now cosine x, I'm going to express that as the Taylor series for cosine x. So I have 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus, and then this would continue, -1 to the k times x to the 2k over 2k factorial and that would continue like that. Okay, so when we go to simplify this, the 2/3 x, and then we would have plus 1/3 x. So now you're basically going to distribute here, right? So on and so forth. So we have 1/3 x minus the x times x squared is x cubed. So we have x cubed over 3 times 2 factorial But now 3 times 2 factorial would just be 3 factorial, right? Or you just write 3 times 2 factorial for now. And then we have 1/3 x times x to the 4th, so plus x to the 5th over 3 times 4 factorial minus dot dot dot. And they only wanted the first few terms, so I think that's enough for now. So if we could simplify that a little bit, what do we end up with? Well, the 2/3 x plus 1/3 x, that's just x. And then we have minus x to the 3rd over, this will be 6, plus x to the 5th over 4 factorial. That'll be what, 24 times 3, 72. And then we have a minus, and then dot dot dot. Okay, so that's good enough for that one. Let's take a look at B. Alright, in B we have e to the x times cosine x. So e to the x, that power series we're going to multiply by the power series for cosine x. Okay, so e to the x, let's remember what that was. E to the x, I'm just going to write the problem here, e to the x cosine x. So e to the x was 1 plus x plus x squared over 2 factorial plus x cubed over 3 factorial like that. And then we're going to multiply with the cosine x. The cosine was 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus, like that. So when we go to multiply these, what we'll end up doing is we can multiply the first series by each term of the second series, right? Or you could do vice versa, whatever you're more comfortable with. What I'm going to do is multiply the first series by each term in the second series. Okay, so first I'll multiply the first series by 1. So 1 times everything. Okay, so 1 times everything is that, so let's write that. 1 plus x squared over 2 factorial plus x cubed over 3 factorial. Okay, next I'm going to multiply everything by negative x squared over 2 factorial. So now we're going to go like this. So that's going to make this, because these are all going to be negatives, let's do this. Let's put a minus here. So now we have x squared over 2 factorial times 1. Okay, and then next we have x cubed, because x squared times x, that'll be x cubed over 2 factorial. And then next we would have x squared times x squared is x to the 4th over 2 factorial times 2 factorial. Next we would have x squared times x cubed x to the 5th over 2 factorial times 3 factorial. So on and so forth. Next, we will multiply everything in the first series by x to the 4th over 4 factorial. So picture like this, where we multiply everything in the first series by... Okay, so that's going to be a plus. I'll start a new line here. Plus, we would have x to the 4th over 4 factorial plus x to the 5th over 4 factorial plus x to the 6th over 2 factorial times 4 factorial, or 4 factorial times 2 factorial, plus x to the 7th over 4 factorial times 3 factorial, dot dot dot. Okay, so from here we could simplify some things. I'll leave this for you guys as an example to finish off. But you'll notice that as you do these, you're left with the 1, the x. Now the x squared and the minus here, x squared over 2 factorial, they cross out. The x cubed over 3 factorial and the x cubed over 2 factorial, they don't cross out cleanly. You're left with a x cubed over 3. And you can easily verify this. You have, I'll do it on the side here, x cubed over 3 factorial, and this would be a minus, so we're talking about these two, but the minus, affecting the x cubed over 2 factorial. So x cubed over 3 factorial minus x cubed over 2 factorial. So that would be x cubed over 6 minus x cubed over 2. And then so we would get a common denominator, multiply by 3 over 3. So x cubed minus 3x cubed over 6, that would be negative 2x cubed over 6, reduces to negative x cubed over 3. Okay, so that's how you end up with this term. And then you could do a similar approach for the next term. You go one more term if you like. Next term would be minus x to the 4th over 6. And obviously these will continue. Okay, so let's take a look at another example. For what values of x can we replace sine x by x minus x cubed over 3 factorial and obtain an error whose magnitude is no greater than 3 times 10 to the negative fourth? Okay. So we could start off by writing the terms of sine x, right? So we know from previous experience that sine x is equal to x minus x cubed over 3 factorial plus x to the fifth over 5 factorial minus x to the seventh over 7 factorial, and obviously continues. So they're saying, for what values of x can we replace sine of x by x minus x cubed over 3 factorial? Okay, so we have that already in here, right? So if we want to think about it, here's our cutoff. So we have done this before with the alternating series, right? We had something called the alternating series estimation theorem, right? So we know that after this series, after this term, let's say, after the x cubed over 3 factorial term, that's not going to be greater than this next term, right? So the sum up until there is not going to be greater than x to the fifth over 5 factorial. So that's what the error is not going to be greater than, right? So the error is not going to be greater than x to the fifth over 5 factorial. Okay, so that would be equal to, well, x to the fifth over 5 factorial would be 120. So that means we could set this up and say the error will be less than or equal to 3 times 10 to the negative fourth, right? That was the obtain an error whose magnitude is no greater than 3 times 10 to the negative 4. Okay, so that means we could say that x to the fifth over 120 so we're going to figure out what the x is then. So it's going to be less than 3 times 10 to the negative 4. Okay, so if we multiply both sides by 120, that means we'll be left with absolutely x to the fifth is less than 360 times 10 to the negative fourth. And then we want to take the fifth root. Right, so take the fifth root. that means we'll have absolute value of x is less than, and we could calculate this. Fifth root of 360 times 10 to the negative fourth be approximately 0.514. And so one final note from the alternating series estimation theorem, because of the x to the fifth over 120 is positive, right? We got the positive sign in front. This tells us that the estimate for sine x for the first two terms, x minus x cubed over 3 factorial, this would be an underestimate to sine of x. Okay. Alright, so that's about it. Feel free to watch the video, pause, rewatch. Any questions, just write me an email. I'll see you guys in class. Stay safe.